Hello everyone, I am Linghang from MIT, and today I will talk about constructing covariant quantum codes using charge-conserving unitaries. This is joint work with Zi-Wen from Perimeter Institute. Let me first introduce the background for this work. Quantum error correction codes protect quantum information by introducing redundancy to the system and encoding the information into a subspace of a larger Hilbert space. Mathematically, if an error correction code corrects some error perfectly, it means that the encoding channel followed by the noisy channel and then followed by some decoding channel equals to the identity channel, so that the output state always equals to the input state. In our work, we consider a specific type of noise, which is the erasure of T-qubits. Mathematically, it takes this form where alpha refers to a set of T-qubits. So this means that with probability P alpha, the qubits in the set alpha get erased from the input. And in the output, we have an additional register which records which sets of qubits have been erased in the process. There is one type of quantum error correction code called covariant code, which is quantum code with some symmetry. To be more precise, we say that a quantum error correction code is covariant with respect to some symmetry group G if the group G could act on the physical and logical Hilbert space through some representations, and such representations commute with the encoding process. So here, if you apply the logical action first and then do the encoding, it's equivalent to do the encoding first and then apply the physical action. We often assume that the physical action takes the following form. It is a tensor product of unitaries over each qubit. And if the group we study is a Lie group, then the physical charge operator, or in other words, the generator, is a sum over local terms on each qubit. Covariant codes are very useful in quantum computing because they have nice properties of fault tolerance. By definition, logical gates could be implemented transversally in the form of a bunch of single qubit unitaries, and such unitaries do not propagate errors. In general, if you have an error on a qubit before you apply a two-qubit gate, then after applying the gate, the error will propagate to both of the qubits in general cases. And that's why single qubit gates are more desirable for fault tolerance. And that's why we want covariant codes in quantum computing. Covariant codes arises in many other areas in physics as well. For example, condensed matter physics, quantum gravity, and reference frame quantum error correction. In condensed matter physics, quantum error correction code naturally arises in many-body systems. For example, for some system that satisfies eigenstate thermalization hypothesis, or ETH for short, eigenstates in a narrow energy band are codes that are covariant with respect to the symmetry of energy conservation. In quantum gravity, there have been a series of papers which have shown that the ADS-CFT correspondence could be understood in terms of quantum error correction codes. As we will see later that there are some limitations on covariant codes, and this is closely related to the conjecture that there is no global symmetry in ADS-CFT. In the theory of reference frame quantum error correction, the two communicating parties do not share a reference frame, or in other words, the basis of their quantum systems are related by some unknown unitary transformation. In this setting, in order to send a message through a noisy channel, they have to use some quantum error correction codes that's covariant with respect to the unitary group. Covariant codes are nice, but they also have limitations. The Eastin-Knill theorem states that a code with a universal logical gate set that can be implemented transversally cannot correct erasure errors perfectly. There is also an alternative version of the theorem, which is more relevant to OR setting. It states that a code covariant with respect to a continuous group cannot correct erasure errors perfectly. The intuition is that the covariance condition indicates that the expectation value of the logical generator equals to the expectation value of the physical generator, which equals to a bunch of local terms. If the system undergoes an erasure noise, then the environment will obtain some of the qubits, and it could measure those local operators to learn something about this value. And as a result, this information leakage indicates that there is no perfect error correction. Then a natural question would be, what about approximate error correction? In order to quantify the performance of approximate error correction codes, we first define a concept called purified distance between two states. It is defined this way, where f refers to the fidelity between the two states. Then we can define the Choi error and worst case error for an error correction code. The Choi error is defined using the maximally entangled state between the logical system L and a reference system R. The logical system undergoes the encoding channel, then the noisy channel, and finally a decoding channel, while the reference system is unchanged. In the end, we compare this input state and this output state and minimize the purified distance between these two over all possible decoding channels. The worst case error is defined similarly, but this time we want to find a reference system R and input state rho such that the purified distance is maximized, and that's why we call it a worst case error. These two quantities will be used to capture the error rate of the code for the rest of this talk. Based on these two error measures, there is an approximate version of Eastin-Knill theorem given by Feist and others, which states that for a covariant code, the Choi error and the worst case error have such lower bounds. This means that there is a limit on the performance for a covariant code, and you cannot decrease the error rate indefinitely. Here, n is the number of qubits, and delta t is the difference between the largest and the smallest eigenvalues of the operator t. TL here is the logical generator, and Ti is the physical generator on qubit I. Now let me explain the main results of our work. We have studied quantum codes that are covariant with respect to U1 group, and such codes encode k logical qubits into n physical qubits. The logical and physical charge operators are Hamming-weight operators, and basically this is the most general form if you only consider local operators. We have shown that for such U1 covariant codes generated from hard random unitaries, which we will explain in detail later, the Choi error and the worst case error saturate their lower bounds with high probability. This means that random U1 covariant codes are typically optimal, and this also gives a randomized construction of U1 covariant codes. Now let the notation Qm to be the m qubit Hamming-weight operator. Then we can define the covariant code in the following way. Consider a k qubit logical state phi, and it will be encoded into an n qubit state phi bar, which equals to this formula. Here, the state psi alpha is an eigenstate of n minus k qubits Hamming-weight operator with eigenvalue alpha, and you have to commute with the n qubit Hamming-weight operator. And such unitaries have to be block diagonal with respect to the Hamming-weight operator. All the codes constructed this way will be called NK alpha code. And specifically, if U is hard random with respect to the subgroup of all the possible unitaries that commutes with the Hamming-Weight operator, then the code will be called NK alpha random code. Now let me present the main statement of our results. First of all, the NK alpha code is always covariant for any choice of the unitary U. Then in the large N limit, suppose that alpha is linear in N with the coefficient between 0 and 1. Then with high probability or NK alpha random code have error rates that satisfy such upper bounds under the erasure of T qubits. The bounds are violated with probability exponentially small in N. And when the coefficient equals to 1/2, or code have smallest error rate, and this saturates the lower bound given by the approximate Eastin-Knill theorem that I have just mentioned. For the worst case error, this is saturated exactly, and for the Choi error, it is saturated up to a constant factor. Before talking about the proof technique, I want to mention a few interesting points about this result. The first thing to do is to compare our results with the quantum error correction code without any symmetry. Suppose that you want to generate a random quantum code using hard random unitaries from SU to the N. Then you can get pretty good quantum codes without symmetry as long as the quantum singleton bound is satisfied. To be more precise, let delta be the difference between the left-hand side and the right-hand side. Then the purified distance is exponentially small in delta with high probability. While for the covariant code, the purified distance is lower bounded by something that is polynomial in N. We will show later the reason behind this difference from a mathematical perspective. Another interesting thing to notice is how to construct such codes efficiently. We have used hard random unitaries in our construction, but as we will see later in the proof, we only need 2 designs, or in other words, some distribution over unitaries such that their first 2 moments matches that of hard measure. 2 designs without any symmetry have been a well-studied topic, and it is known that they could be constructed using 2 local random gates. There have been many papers that study the number of gates needed to construct a 2 design on various interaction geometry. However, in our case, we need 2 designs with U1 symmetry, and it is not clear if they could be generated this way using local circuits. Finally, our result could imply interesting properties for the unitaries that we have used in our construction. Hard random unitaries have often been used as a model for chaotic quantum systems, and therefore, the hard random unitaries with U1 symmetry that we have used in our construction underlie important models of chaotic systems with energy conservation. So in this sense, our results not only provide a construction for optimal covariant code, but it also reveals fundamental properties of such unitaries, and it has potential implications for chaotic systems. For future work, the first interesting question, which is also what I am currently working on, is to extend this result to more complicated symmetry groups, especially SUD. In that case, all the logical operations could be implemented transversally, which could have potential applications in fault-tolerant quantum computing. The second question is about decoding. We have not discussed decoders yet in our paper, and maybe they could be related to Yoshida-Kitaev protocols or path recovery map. And it would be nice if we can have some decoder that is efficient. The third question is about local random circuits with symmetries in general. According to a paper by Marvin, such circuits are not universal, so they do not converge to T designs for arbitrarily large T. However, it will be still interesting to see, for example, if there are 2 designs. And even if they are not, it would be interesting to ask if they could lead to good error correction code in our protocol. Finally, let me talk a little bit about how we obtain such results. The first ingredient of our proof is the decoupling theorem and the partial decoupling theorem. Decoupling theorem studies the following situation. So you have an initial state phi AR located on the joint system of A and R. Then the system A undergoes a hard random unitary UA, followed by a fixed channel T that maps system A to system B. Then the expected one norm distance of the result you have obtained here and its average over the hard measure is upper bounded by this following quantity. So in some sense, the decoupling theorem is a concentration of measure inequality for random quantum states. The partial decoupling theorem works similarly, but this time, instead of a fully hard random unitaries, UA takes the form as the direct sum of tensor products. And similarly, we can get an upper bound for the expected one norm distance in this formula. Our second ingredient of the proof is the perspective from complementary channel. The joint action of the encoding channel and the noisy channel is a CPTP map from the logical system L to the physical system A. And it could also be viewed as a unitary from L to A and some environment E, followed by a partial trace over E. Then the complementary channel is defined as a mapping from L to E. The performance of an error correction code could be characterized by the complementary channel through this formula. Here is the original definition of the Choi error, and here it equals to the purified distance between the complementary channel and a constant channel T zeta acting on the input state, which is the maximally entangled state. The constant channel T zeta is defined to be the channel that always outputs the state zeta regardless of the input state. There is also a similar result for the worst case error. Intuitively, this means that a code works well if the environment does not learn much from the encoded information. This also formalizes the information leakage intuition we talked about in the beginning. To give an upper bound for the Choi error, we first use the complementary channel formula here, and then break it into two terms using the triangle inequality. The first term involves random unitaries, and it could be bounded by partial decoupling theorem, and we can show that it is exponentially small in n on average. The second term is the main contribution, and by direct calculation, we can give an upper bound for it. It is interesting to note that if we consider the random codes without symmetry, then the second term naturally vanishes, and that's why we can always get random codes with exponentially small error if we do not have the U1 symmetry. In order to get an upper bound for the worst case error, we will need this following lemma about deterministic codes. We first fix a set of logical bases X and define the state rho XX prime this way using the complementary channels. Then suppose that all the rho XX are close to some fixed state and all the cross terms rho XX prime are small. Then there exists some upper bound for the worst case error. However, we are dealing with random codes instead of deterministic codes. So we define the quantity rho XX prime average as the quantity rho XX prime average over the randomness of the construction of the code. By direct calculation, we can show that this average quantity satisfies all the requirements in the lemma given on the last page. We also know that the random quantity rho XX prime cannot deviate from its average by too much due to the partial decoupling theorem. So finally, we can use an union bound to show that with high probability, the quantity rho XX prime associated to a random code also satisfy the requirements in the lemma. In summary, we have constructed quantum error correcting codes that are covariant with respect to U1 symmetry. And then we have also shown that the Choi error and worst case error of such random construction typically saturate known lower bounds. Thank you for your attention.